Good evening. The continuation of the session mobile radio propagation. Already we have discussed the effects of diffraction in the previous class. Diffraction is nothing but bending of waves. This happens due to the effect that once the wave hits on a sharp edge, the waves get diffracted or bent. So I understand the effects of the diffraction or the phenomena. We shall consider a scenario. Diffraction in the context of wireless communication that refers to the bending or spreading of radio waves around obstacles or sharp edges in their path of transmission. It is a fundamental phenomena in wave propagation and can significantly affect the coverage and performance of wireless communication, especially in scenarios where there are obstacles such as buildings, trees, mountains, or any other irregularities obstacles. The important points that shall be considered in understanding the diffraction is wave behavior, Huygens principle, aperture effect, edge diffraction, Fresnel zones, impact on communication, and mitigation. Understanding the behavior of diffraction is essential for designing efficient and reliable wireless communication systems, especially in urban and suburban environments, where obstacles are prevalent. Engineers use propagation models and simulation tools to predict diffraction effects and optimize the system performance accordingly at a predefined conditions. So, one such kind of model so as to analyze the diffraction is knife edge diffraction model. This model is useful for estimating the signal attenuation caused by diffraction of radio waves over hills and buildings in essential predicting the field strength in a given service area. As a starting, the limiting case of propagation over a knife edge gives good insight into the order of magnitude diffraction loss. When shadowing is caused by a single object, such as any building, the attenuation caused by the diffraction can be estimated by treating the obstruction as a diffracting knife edge. Shadowing, what is it? Which is nothing but the shadow of the building or trees. Shadow, in the sense, we should not consider the building shadows of uh, everywhere. Only the building which is in our purview shall be considered for taking the shadowing effects. Right. This shadow region is otherwise called as a dark region. So consider a receiver at a point R located in the shadow region. The field strength at point R is a vector sum of the fields due to all of the secondary Huygens waves in the plane above the knife edge. The difference between the direct path and the diffracted path coalesces path length. So this is also represented with the terminology path difference del is equal to h square d1 plus d2. Why? Because in the drawing we can see the obstacle is present in between the transmitter and receiver at a distance of d1 from the transmitter and at a distance of d2 from the receiver. So here we are considering the two distances for analysis. Therefore, del is equal to h square d1 plus d2 divided by 2 times of d1 d2. The corresponding phase difference will be phi is equal to 2 pi del by lambda, which is equal to 2 pi by lambda. Substituting for a del value here gives this result. Fresnel Kirchhoff's diffraction parameter. This is used to normalize the phase term and given as the factor which is equal to h root of 2 times d1 plus d2 divided by h d1 d2, which is approximately equal to another value. And this also gives the phase angle pi by 2 into the factor whole square, where alpha is another approximation which is represented here. This is the pictorial representation of a knife edge diffraction model. See here, the diffraction model, assuming the obstacle height is greater than the height of the transmitter and receiver. Here, the height of the transmitter and receiver are assumed to be equal. And the difference in height is called as sharpness of the object. Sharpness of the object is nothing but the H obstacle minus H transmitter or H receiver. This is the sharpness of the object. So the angle of incident exactly at the sharp edge is represented as beta, and the angle of incident of the secondary wave at the point of receiver is termed as alpha, and the ray which is diffracted is termed as gamma. Next is Fresnel zones. Fresnel zones. As we mentioned here, once the wave hits the sharp edge, wavefronts are formed continuously. As many signal strength is available, that many number of secondary waves or wavefronts have been generated. If we consider the wavefronts to form a closed path, that can be represented as Fresnel zones. See here, all these wavefronts form a circle, and that is named as Fresnel zones. Fresnel zones represent successive region where secondary waves have a path length from the transmitter to the receiver, which are n lambda by 2 greater in path length than that of the LOS path. The plane below illustrates successive with Fresnel zones. Next one is multiple knife edge diffraction. This is nothing but instead of one object, here many obstacles can be placed between the transmitter and the receiver. This is multiple edge diffraction. Obstruction 1 and obstruction 2 and single obstruction, just for an example. The next topic is scattering. Scattering, as the word infers, it is distributing of waves or forming many number of waves. Scatter is nothing but occurs when the medium through which the wave travels consists of objects with dimensions that are smaller than the wavelength of the wave which is incident, and where the number of per unit volume is very large. Scattered waves are produced by rough surfaces, small objects, or by other irregularities in the channel. Scattering is usually caused by trees, lampposts, towers, etc. Received signal strength is often stronger than the predicted by reflection diffraction models. The EM wave incident upon a rough or complex surface is scattered in many directions and provides more energy at the receiver end that would have been absorbed is instead of reflected to the receiver. Flat surface means the electromagnetic reflection is in one direction. If it is rough surface, the scattering is in many directions. Phenomena where the wave is directed to multiple directions is called as scattering. So scattering, the effect of scattering on a smooth surface, on a rough surface, and also a rougher surface is mentioned here. If the wave is incident on a smooth surface, then there will be a diffraction in a specific direction. If it impinges on a rough surface, then there would be a range of diffraction. If further rougher, then the scattering is widened. Therefore, the roughness depends upon the surface height range, angle of incidence, and wavelength. Hope you have understood this session. Thank you.